All right, good evening, everybody, and welcome. We're starting off the year with a high energy topic, and I'm sure it's going to be a high energy presentation. I'm looking forward to it. Over to you, Christo. Let's go for it.
Thank you so much, Derek, and thanks everybody for joining. It's my pleasure to be here. Thanks for the invite, and let me also start off by saying a wonderful new year to everybody. May it be a wonderful, fruitful, and blessed year. So I have the pleasure of speaking to you about gamma ray pulsars, which is the stuff I've been working on for the past 20 odd years or so. And I'm gonna try and keep it light, pun intended, so that we can all enjoy. But if you have questions and they're not too difficult, I can try and answer them, but they are still open questions in the field, as it should be, because it's an active field of research. And I decided to title this Treasures of the Dark Skies to be a little bit poetic, but also to just intimate that this is really very unique objects, spatial objects, and you can do a lot of physics with them. They can also be used as tools because they are so accurate clocks, such accurate clocks that you can really use them to measure things. So we'll get into all of that. At the top right, I'm sure you know what a pulsar is, but that's a nice cartoon version showing that in an idealized case, it's a rotating sphere with radio emission, for example, emanating from the poles, or close to the poles. There's also other photons coming from these objects, but we'll talk about that, especially gamma rays. But when the line of sight intersects with this beam, or the beam with the line of sight of an observer, you'll see a pulse. So that's why I have this lighthouse to the right, because it's similar to that, and it's just much faster, the rotation, because you even get up to the fastest ones are rotating at 1.4 1.5 milliseconds. So that's like hundreds of times, almost up to 1,000 times per second, these massive objects. And to the left below, you'll see the double torus structure, which is the wind nebula of the famous Vela pulsar. We'll talk about that a little bit, and you'll see to the top right of that picture, there's a corkscrew jet, they call it, because it's like rotating like a corkscrew, and really lots of things that one can study and interesting things. So let me jump in with a few definitions, and if I go too slowly, just tell me and I can move on fast and quick. So just to start again, a pulsar is a pulsating star. And our cartoon picture is that you have a sphere of matter, and we'll talk about what's on the inside in a second. But it's a neutron star, and it's surrounded by a magnetic field. Now, in this picture, this is a nice textbook dipolar field, but we believe that this is not actually the case. They might be multipoles or some deformations to the field, but in essence, it's a dipolar structure. And then you get particles and you get photons from this star, this laboratory. What you can also see is the light cylinder, and that is this gray object, and that is just a mathematical way of saying that there's a distance from the star where co-rotation becomes equal to the speed of light. And so beyond this light cylinder, you cannot have co-rotation anymore, because that will violate Einstein's theory of special relativity. So what happens is that the nicely closed field lines are flung open, and particles are streaming along these field lines outward, blowing a bubble that we call a nebula. And so we'll talk also in a second about different types of pulsars. And we often see that these pulsars are surrounded by this nebula or cloud-like stuff. And it's like a bubble being blown by this particle wind. It's similar to the solar wind in a sense, but it's just relativistic particles. So it's not slow, it's a fast wind, very fast wind, and low density wind. So just to orientate ourselves some more, as a modeler, I'm a theorist or a modeler. We like to think in terms of little boxes. So what you have are things you can model and measure. We try to make the models in a way that we can test them with observations. So if you consider a cube, and we label each side according to different variables. Now, on the front, let's say, right face of this cube, we call that phase, or that cyclical time. So these things are rotating, but they are repeating. They have repetitive emission or structures, so that is cyclical time. Then there's an energy dimension. We are talking about gamma ray pulsars specifically, but these things radiate across the band, the wave band. So you'll get radio emission, X-ray emission, optical emission, infrared even. So lots of different energy photons. And then we are an observer at a specific colatitude with respect to this pulsar, but that can change. So that's a variable, and we call it typically zeta or colatitude. Now we can't see the whole beam of a pulsar. We just see a intersection of our line of sight with this beam of the pulsar. So we have to make some cuts, and so that's how we model these. We model everything and then we make cuts so that we can compare with observations. So if we cut in a certain latitude, that means it's a specific observer. Let's say we're sitting at 45 degrees. And then let's say we look at a phase of 180 degrees if you think about 0 to 360. So you've cut something, and what changes is the energy. And so what you have is, in this case, I will tell you about the analogy, but we have photons versus energy. Now, if you think about finance, you might have a chance of occurrence, and oftentimes in science you get this. It's a statistical type of measure of the chance or frequency of occurrence versus some other variable like returns. And you can see that the money is growing nicely, and then later on it might drop or something like that. So in astrophysics and all over space physics, you find that spectra actually have a lot of information that they carry. And so the number of photons per energy bin versus energy, that's what we call a spectrum, a photon spectrum. Now also light curves, I'm going to talk about light curves later on. This is basically the flux versus phase. So again, you have to cut along a certain observer because we will see different light curves according to our geometry or orientation. And then if you integrate over some energy band or at a specific energy band, you take the number of photons you have, but typically it's an energy bin. Then you get something, and I'll show you the pulsar version, but this is again financial stuff. So you get some kind of variable that's changing with time. That's what we typically call a light curve, and because this is periodic, you'll see a certain little signature from each pulsar, which is quite unique. And I like to think of it as a fingerprint of the pulsar because they all have slightly different light curves. And these change with energy. So, yes. Okay, a little bit of history, what happened, how whether they discovered, and so on. So in 1967, there was a graduate student. Her name is Jocelyn Burnell nowadays. She was Jocelyn Bell at the time. She was a grad student at Cambridge, or was it Oxford, I believe, one of the two. Sorry, I forget now. I think Cambridge. But anyway, they were building this, you can't really say it's a telescope, maybe it's a scintillator device measuring scintillation. And what she saw, if you look at this plot with the red line, there's little dips that you can see. Now, she had to go through miles and miles of these paper rolls. It's almost like a seismology type of measurement, but it's not seismology, it's radio waves. And she saw these little, it looks like dips, but actually this is a inverse axis, so it's little peaks or pulses. And what she saw then by eye was that there's something there and it seems repetitive. And so she told the supervisor, and they looked again, and they nearly missed it. You can read the story online. It's very interesting, fascinating. There were a few people who got near discoveries, but she actually got a discovery, and she nearly missed it herself. And they saw that this was actually linked to the stellar or the sidereal time. And so it was an astronomical thing. It's not the terrestrial effect. And so they saw the first pulsar. So they kind of jokingly speculated that this might be an alien. So they called it Little Green Man number 1. But of course, many of these objects have been found since and from all over the sky. So we know that this is a natural phenomena. And in the first year of discovery, there were already 100 theoretical papers about what this could be and what this could not be. And nowadays, we really believe that these are neutron stars. So I'll get back to that. There's another picture of sifting through the data. Now, just to show you some nice pictures, if they want to work. This is from NASA. And so we work on pulsars as well with our collaborators at NASA. This is again the beams of radiation emanating from the poles of the star, but of course that's more the radio type of beams. The gamma rays come from elsewhere, we think. And we'll talk about the diameter. It's about 20 kilometers across, and you squeeze the solar mass into that object. So it's really, really compact, meaning that gravitational GR effects, general relativity effects, become important. You can see it spinning, and it's slowed down for us to at least follow, but these things spin very fast, as I told you. From far away, you see this blinking effect. So you see the light curves. And these pulsars are so heavy that they sometimes capture another star and they eat its mass. So this is called accretion. And the mass accretion happens, and then you can actually have streams of mass impacting and impinging on the stellar surface, creating hotspots that you can also see, type of a sinusoidal type of wave that you can see. So where do they come from? Well, normal stellar evolution, if you have a heavy star and you have a supernova, that happens because you use up all the fuel that's burning, the nuclear burning inside, then what's left oftentimes is a pulsar. And it's the solar mass, as I mentioned, that's packed into a 10-kilometer radius. So a very, very compact star. Now, why gamma rays? Well, that's just the field I inherited. But we are looking across the electromagnetic spectrum, so we're not just gamma rays, but that's the focus for now. So if you look at the visible light, of course, this is about 1 electron volt in energy, and gamma rays can range from GeV to TeV energies and higher, even up to PeV nowadays. So this is really like 1 billion to 1 trillion and more times energetic than visible light. So yeah, we really work with photons, and they actually come one by one and not so often even. And you have to accumulate over many years to see a good statistical fit or data accumulate, and then you see the light curve. Let me briefly mention that it's not just photons we're looking at. Nowadays, the hot topic is multi-messenger astronomy. And this actually alludes to the fact that there's different messengers or particles coming from these astrophysical sources or waves. So we spoke about the photons and all the different types, radio, microwave, optical, X-ray, gamma rays, etc. But you also can get neutrinos, very light mass particles, weakly interacting ones. We get cosmic rays, we believe, from pulsars like maybe hadrons or electrons, positrons. And then these pulsars can be used as tools to measure gravitational waves, which we will speak about also in a second. So it's really multi-messenger objects along with other objects in the sky. And I also said in the abstract that this can cover a range of physics topics. So I'll try to give you a sense, but it's so wide that I can speak for 2 hours, but I don't want to bore you with 2 hours worth of information. But let's look at gravity. So these pulsars are like little clocks, very compact, very, very stable. The millisecond pulsars, the old ones, are stable up to, I don't even know, I think the 15th decimal maybe, or something like that, the 20th decimal after the comma. So very, very stable. The rival atomic clocks, maybe 14 or so decimals, let's say. And so what happens is we are surrounded by, or we're living in 4D space-time continuum. And if there's a gravitational wave that happens to be passing by, then we can be measuring all these pulsars. It's called a pulsar timing array. And if this wave passes, it slightly stretches space-time, or it shrinks it, and so on. And so you can see that from the fact that you have deviations in your timing of this array of pulsars, you can actually detect a wave passing by. These waves are predicted by Einstein's theory of gravity. They move at the speed of light, and in this case specifically with these scales, you're looking for nanohertz waves. And we're hoping to measure these waves. We are getting closer and closer. This is a worldwide endeavor, and we're above 4 sigma at the moment, but not yet 5 sigma in significance. So basically, what would create these waves? Well, we think that there are black holes that are colliding and merging, as we've seen from the LIGO measurements and the Nobel Prize that went to them. And so they've measured this actually, and a lot of distinct characteristics that tell us that the masses of the black holes, etc. And so if you have lots and lots of these things merging, you would get a stochastic background of gravitational waves. And there were some clever people that decided to model this and to theorize about this. And so if you look at this graph, what they predicted, Hellings and Downs, were that the interaction, should be a function of separation of pulsars. So if you look at the zero, there's a good correlation, rather, not interaction, correlation. And if you go to 90 degrees, then not so much. And again, 180, it picks up again. So this is a very telltale signature that people are looking for. And there's the data on top. It's not just, not yet 5 sigma, as I said, but we're getting closer, and people are stacking all the data from different pulsar timing arrays to try and get closer and closer. In our country, we have Meerkat, the radio telescope, and there's the so-called MPTA, Meerkat pulsar timing array, and they have really exquisite data. They caught up with all the other people. They were doing science for 15 years, and we, in the last 5.5 years, actually got very good results due to the sensitivity of the telescope, and we are actually now contributing to this global science. Just to show how big and wide everything is, excuse me, the pulsars are about a few kiloparsecs away. And this is 10 to the 21 centimeters, but okay, it's a few, so it can be, 1 or 2 or so sub. So lots of zeros there. It's a big scale. This is astronomy in the solar system and beyond. In the galaxy, actually. So they are actually, just for interest sake, pulsars in other galaxies too. We've been seeing them, the closest ones, Large Magellanic Cloud and so on. But for now, the local ones are the interesting ones. We can actually see them, measuring them very exquisitely. So yes, GR, gravitational theory, you can use pulsars to really measure this very finely, the masses. Look at the MA and MB with all the digits there. Really great measurement. And there's the zoom in, where these things, all these theoretical curves coincide. This is on the right, a famous a measurement of the shrinkage of the orbit of a binary system due to gravitational wave emission. And this led to the Nobel Prize for Hals and Taylor. So this was the first indirect measurement of gravitational waves, and we're looking to measure this more directly now. What's inside? Well, I'm not totally an expert there, but there's people just spending their careers figuring out what's going on inside, and this is covering nuclear and quantum mechanics. So protons and electrons combine to form neutrons. This is the densest form of matter. And so the Pauli exclusion principle applies, and the neutron degeneracy pressure halts gravitational collapse. So you stop this collapsing star from becoming a black hole, and you have a neutron star with a superfluid, meaning no viscosity, and a superconducting fluid, which means no resistance. So yes, it's really complicated physics going on if you follow this type of research. And people are measuring this. You remember from school time that the ideal gas law says PV equals nRT, pressure, volume, temperature, all of these things are related. Now we want to figure out what's the equation of state of this superfluid in the neutron star. And so if you look at the right-hand side, there's lots of theoretical work giving you different options for mass versus radius curves. Or to the left, it's pressure versus density. And so if you measure the masses of pulsars, as they've done, and you end up measuring, let's say, 2.2 solar masses, you're already excluding quite a few theories. Those are the grayed out ones. And then there's a few more contenders left. So this is really interesting to use pulsars to constrain equation of state of neutron superfluid. Let me skip this one in the interest of time. And then what's outside? Again, quantum mechanics, electrodynamics. Outside, we think there are magnetic fields, electric fields, pair production, which means a photon moves through an intense magnetic field and it pair produces, forming an electron and a positron. And you have a whole cascade of this happening, lots of pairs, and then also you have particle acceleration, you have flow, currents, all these things. Very tricky stuff to calculate. Lots of things you have to assume, and from first principles, different types of big codes, and then radiation, of course. That's what we see. So on the left, you see X-rays from a hot spot on the polar cap. And this is the model where you have these hot spots that you infer from the data fitting. And then you have gamma ray data. The model is not perfect there, but it's kind of a double peaked structure. And we're still sorting out exactly what the B field structure should be to figure out and reproduce the data. Just to mention, in this vein of talking about multi-messengers, we expect that the pulsars can contribute positrons to our local interstellar medium, and we've been measuring the local spectrum, and this is an old calculation we did for binaries and isolated pulsars, and the so-called positron ratio, or the excess is the excess of positrons if you divide by the total leptonic flux, and this is a function of energy, and this is rising, counter to expectations that the people had, where this was the background should just be dropping. Now this is a rise in the excess. So yes, we think that pulsars can also contribute to this. And then there's lots of different types of pulsars. I don't want to spend too much time on this one, but there's a nice plot that we call the PP dot graph. This is the period and the spin down period, so the time derivative of period. And the period changes because this pulsar is losing energy. So basically, if you lose energy, then it will spin slower. And so if you plot this, you see that there's two groups of objects, the younger ones and the older ones. And there's a lot of physics to explain in this graph, but you can see that there's about 2,000 young pulsars in the field, and actually maybe slightly more, and 500 old ones, and they're in binary systems, mostly these old ones, the millisecond pulsars. There's also quite a few of them in globular clusters, and since we started with about 7 of them in gamma rays. Now there's more than 300. So it's really an explosion of pulsars, and it's very interesting. They have different parameter spaces or sets where parameters where they occupy space, and so there's different types of these things as well. And so let's look at pulsar in nebula. I told you that the central one is the pulsar, and they blow a wind of particles. And so what we typically see, this is the crab, famous crab pulsar. You can see how it's blowing a wind, and then you see the torus forming and the jets. So this jet torus structure seems ubiquitous, and it's a very dynamic thing. So try and model this. This is really not so easy. People have been trying for decades, and they are making progress, but it's still tricky. And this is the velar pulsar. Just listen. If you convert the emission to sound, this is what it sounds like. So basically, this is a rotating neutron star, and its period is 89 milliseconds. So you can imagine how quickly this is rotating. You hear a lot of pulses in a sense. So we're converting electromagnetic radiation. It's not really something you can hear, but you can convert the signal into a sound just for the sake of analogy. And this is the nice, very thin radio emission that you measure, and it's a stacked type of emission, because that's where you get your signal to rise above the noise. So different types of pulsars. This is an interesting one. As I told you, pulsars can be in a binary system, and they can kind of consume their mates. They eat them by accretion, and that's why cleverly people call this spider binaries. It's like a black widow and a red back binary, and it's a low mass star in close proximity to this old pulsar. And we have now about 50 of them in the galaxy that we've detected, and we're modeling them because you can learn a lot from the physics if you model all these signatures that you see. There's a recent development where people have seen a white dwarf that's actually acting like a pulsar, so it's dubbed a white dwarf pulsar. And my ex-student has modeled this, and look how beautifully this is a geometric model of the polarization versus phase, and you can really pin down the geometry alpha and zeta, which is the magnetic inclination axis or angle, and the observer angle to a few degrees. So really, really interesting. And this is in the optical band. We see this typically in the pulsar case in the radio band and for a much smaller phase range. So this is a very unique system, and they are finding more of them. I think there's now about 2 or 3 of them. So a new class of pulsars that are being established. So I'll quickly skip through a few basics. If you look at let's call it the ice skater or ballerina type of person, they make rotations, and when they make their body small and they make their eye, they change the eye, the moment of inertia, then of course the omega will increase. So because L is constant, the orbital momentum, the angular momentum, sorry, still slow. I still have to get used to the new year. So the angular momentum is constant, so I times omega is a constant. So if I goes down, omega goes up, and that's what happens with the pulsar too. The star implodes, and so I becomes much smaller, and you get the omega increasing a lot quickly. And also, there's an analogy with a unipolar inductor. If you rotate a disk in a static magnetic field, you can set up a potential difference between the axis and the rim. Now, this is not a perfect analogy because the pulsar is not rotating a conductor in a static field. The field is co-rotating with the star, but still the physics seems similar, and you can actually create an electromotive force. This force pulls out charges from the star's polar cap surface, and then you create a current, and this is like a gigantic circuit in space, and then you get radiation, dissipation of energy. And as somebody said, it's actually quite simple. Your energy, you understand how the pulsar is spinning down, but the difficulty lies in the wires. There are no wires connecting this potential difference. We have plasma, and that's where all the difficulty comes from. So we're trying to figure out, after so many decades, what's going on in the pulsar. They are very extreme objects, as I mentioned. They can fit in a city like Chicago, but they carry the mass of the sun. So very massive, very small, compact, very dense, very stable. And some of my colleagues have made a simulation of a pulsar where they pull out charges and they have pair production, all these type of things. And you will see in a second that if you zoom in, it's a whole interesting and intricate current flow that happens. And these particles, leptons, they create gamma rays, for example, and other photons that we see and have to explain. So the red ones are positrons, and I think the blue ones are electrons. And so this is the B field. And so you can see there's really some detailed modeling going on, and we are trying to understand this better and better. So this is what they call the current sheet. I like to call it the ballerina skirt. It's also like the heliosphere, same in a pulsar, and that's where they call it the neutral wavy sheet, I think, in heliospheric physics. So we call it the current sheet, and that's where we think things are happening. And so models have changed over the years, but this is an important region now for creating gamma rays. So there's different regimes. You can go in the 50s, there was a solution of the B field, and it was called the vacuum retarded dipole. So there were no charges, no currents, and you get a B field, but that's all. So that's not really a pulsar. And then we have the force-free magnetosphere on the other end, where you have lots and lots and lots of particles, but no electric fields, and so no acceleration, no gamma rays. And so we think the truth is somewhere in the middle, and you have to have big codes, we like to call them non-ideal MHD codes, to have charges, currents, and acceleration. So people are really using big computers to try and solve this problem. This is some of our own work, where we have a change in alpha, which is the magnetic inclination angle. And then you have photons. You see those dark spots, they are the polar caps. And as alpha changes, then these things move in phase space. This is co-latitude again versus phase. And the bright yellow spots are where you have photons, and they form so-called caustics. So due to special relativistic effects, these photons bunch in a phase and in certain regions of phase space. And so if an observer looks at the pulsar beam, then you have to make a cut through these caustics, and then you see the light curve. So basically, as shown here, if you have a fixed observer at, let's say, 40, 45 degrees, then you cut two caustics and you'll see a double peak structure, for example. So that's just our theoretical explanation of how these things work. But of course, you have to make lots of assumptions and fit data and refine your model. And the caustics, you can think of caustics in a swimming pool. It's not exactly the same, but similar, that you have these photons that are squeezed in certain phases or directions, and those are brighter spots. And so if you make a cut through this plane and not look at all the caustics at once, but make a cut, then you'll see these peaks. And that's how I think caustic formation is creating peaks. Now, for different observers, since we are academics and we can just play with our models, you can just have a look from all around, and you'll see different types of shapes and sizes coming out for your light curve. And so if you fit these, we call this an atlas. You make a whole atlas of light curves, you fit them to data, and through that you can try to understand all the pulsars you can find to model and see if you can infer trends in the geometry and otherwise in the spectra and so on. So there's lots of instruments. We all know about Meerkat, which is at the moment 46 dishes strong, and it's an array of dishes. It will be integrated into the mid-frequency component of the SKA eventually. And so there's a few experiments running on Meerkat that are linked with pulsars. One is called TRAPM, transients and pulsars with Meerkat. They've already made about 300 discoveries. Meertime is timing 1000 pulsars to test gravity. As I mentioned, gravitational waves with the PTA, a pulsar timing array. And then there's Meertrap, also timing pulsars and transients and working with the optical Meerlicht telescope to try and see if they can find periodicity and transients in the sky. And the future will have many, many Meerkats. Meerkat is a pathfinder for this SKA that's coming, that will dominate the radio scene for the next decades. And it will be a square array, so a square kilometer in area. It will be the most sensitive telescope in the world, and it's hosted by South Africa and Australia. Eventually, we'll gear up from 64 to 3,000 telescopes with an incredible angular resolution of 50 times that of Hubble. And so there's a lot of pulsar science to be done. This is an old paper, but I'm sure it has been updated. And I'm not going to go through this one by one, but there's lots of potential for discovery of pulsars. Look at that. They estimate 50,000 new discoveries. At the moment, we have about 3,500 pulsars. Now think what you can do with 50,000. And I think you would need machine learning and big data tools to figure out what to do with this and extract science from that. And also you can use pulsars as tools to figure out physical conditions and gravity conditions and so on, gravitational waves. Then there's NICER. Very interesting. It's a mission on the International Space Station. And the aim is to measure the neutron star radius to within 5%. And they've been making some progress. And so, yeah, X-ray, maybe I can show a picture later if I remember. But they've been measuring the light curve in X-rays, and from that you can infer M versus R plots. And if you have an independent measurement of the mass, then you can measure the radius very exquisitely to a very good accuracy. So there's gamma rays, there's optical, and there's Hess. So in the abstract, I was also asked to to talk about his results on Pulsars. I will do that. We've been part of his for the past 20 years, and this is our neighbor sitting in Namibia. There's four 13-meter dishes and one big one, the 26-meter dish. And yeah, really, really interesting science coming from his. And so the newcomer, the future of Cherenkov telescopes would be the Cherenkov telescope array, which is the CTA. That's almost like the SKA of gamma ray science. And they want to put about 100 of these telescopes side by side in an array with large and medium and small sizes for different reasons to optimize the sensitivity across the waveband, the energy band, and lots of people involved, lots of scientists, about 1,000 or so, or more actually. And this is the future. And so, yeah, just to mention LASO, which is an existing facility in China that detected PeV photons. So these ones will go to 100 TeV, but this is PeV, so it's 1,000 TeV. Bevatrons. So it's really, really exciting stuff. The Crab Nebula, they got a photon that was like 0.88 PeV, very close to 1 PeV. Very interesting stuff. And then neutrinos, there's a big ice cube installation. It's called Ice Cube, but it's a cubed kilometer installation in the South Pole, and they are measuring neutrinos. But let me quickly dwell a little bit on his results. So if you look again at the spectrum, as I mentioned, it's photon flux, or this is F-nu, it's more of a energy flux versus frequency or energy. You can see it's a whole broadband measurement with all the different telescopes, and this is for Vela. And so we're focusing on the TeV part, so it's not even shown on this old graph. So you can see all the light curves, flux versus phase again. This is a double rotation, so you'll see a repetition of the pattern. And this changes across optical to X-rays to gamma rays if you go from bottom to top. And so this is now measurements by Fermi, which is a GV instrument. And you can see how the little details change. If you go from, again, the bottom to the top, you go from lower to higher energy. And you can see the first peak starting to disappear. The second peak remains. There's a third peak, this little thing in the middle that moves to the right, etc. So there's a whole story to explain there. So what did HES find? So with a big telescope, it's called HES2, they found basically the same as Fermi. They could measure the tail of the spectrum of the GB pulsar, and they found also to the right that there's a light curve. Sorry. Excuse me. Just give me a second. Okay, sorry, I hope you can still hear me. So you can see to the right that the second peak is coinciding with the GV1. So Hayes and Fermi found the same thing basically. But the very exciting stuff, this is not so exciting, is that they found 20 TeV pulsations from this pulsar. This is really, really unexpected and very large. People have thought about this in the 90s, and then they never measured this. So they started adjusting their models and not expecting this anymore. And then suddenly we found it at a very low flux level. So this constrains the energy of the particles to this Lorentz factor of 4e7. Really, really high energies, TeV energy particles. And so it's a hard spectrum. I'll show you pictures now, and it's phase aligned with the GV light curve, as I showed you. So it must be the same source with the same periodicity, same spatial origin of the photons, or at least it's beamed in our direction. And so we can also get flux constraints and model this. So we found that in the old days, we thought that the gamma rays were coming from inside the light cylinder, but now exclusively or very clearly, these things must come from beyond the light cylinder. So you can see that the second component in the blue is popping up now, in addition to what Fermi has been measuring for lots of pulsars to the left, this GV peaked spectral component. For Vela, there's a second component, and this is really interesting, and you can see that we find the second peak showing up in the right. And if you make a cartoon version of this, you can see again the light cylinder and all these different old models, the blue and the yellow and so on. But now this is extending beyond the light cylinder. We have co-rotation of the particles breaking down and then moving into this current sheet with its plasmoids and all kinds of motion. And so the theorists are still trying to figure out exactly what's going on, but this is an exciting problem. And so some colleagues of mine have also worked on this. And we have this very broadband model. I'm not going to explain all the nitty-gritty of this model. There's lots to talk about, but you can see the rightmost component, this yellow one. This is the new one that was measured by Hess. There's the data, the blue, and the spectrum, and this is the model. And so we kind of have an idea what's going on there. It's inverse Compton. So we have very high energy particles giving you the magenta spectrum, and this is upscattering the synchrotron emission, and you get SSC, synchrotron self-Compton. Also the light curves, there's the data to the right, and to the left we have the model. It's not perfect by any means, but you can see in the optical we have double peak structure, then more widely spaced, then the first peak disappears, and then there's just one second peak remaining at highest energies. So the model can capture some of these things, the phenomenology, but we're still working on more to understand more. Fermi-LAT, Large Area Telescope, is the GV one that I've also been working on. And again, for Vela, as we mentioned, if you go up this graph, up in energy, there's a change in the relative flux of the two peaks. The third peak is moving to the right, and the widths change, etc. So this is all just shown in a different way, where energy is on the y-axis and the pulsar phase, and there's the second peak remaining. So we've modeled this with my previous student and figured out that this is practically due to the geometry of the magnetic peak, the magnetic field. And so you have a slightly different cutoff in the spectrum, and this tells you why, as you go up in energy, the first peak drops out and the second one remains for a little while longer. So really interesting modeling. I could talk about the fundamental plane, but I will just mention here that with basic scaling arguments, you can get an expectation for how the gamma ray flux or luminosity should scale, and this has been measured, and really this is close to the prediction. So this pins down the emission mechanism to be curvature radiation. So there's a whole debate in the field about what this might be, but this is a strong piece of evidence in favor of curvature radiation. And then there's lots of trends we see. I'm just going to flip through a few pages here to show that there are some models that can explain some of this geometry. The delta-delta relation so-called. This is the phase between the radio and the first peak of gamma rays, and then the separation between the gamma rays. And there's a trend we see, and we can explain this in our geometry. So we think we have some feeling of what's going on. And then let me close by saying that there's some interesting developments in the field. People are using machine learning and graph theory and all kinds of things to try and figure out if we can find trends in the population and plot them differently and characterize them differently and understand population-wise what's going on. Also, neural networks, these models are really becoming sophisticated, and you need a lot of computer time to calculate them. And so if you can use machine learning to make this faster, then of course you do. So in this case, some of my colleagues got a speed up of 400. So you can think that your computer code might have taken 400 days, now it takes 1 day. That is really amazing. So machine learning is also entering into pulsar science. And I just wanted to show you that in our small group in Potchefstroom, I just had a meeting with all my students and postdocs, and we're about 10 people. And these are all the many things we want to work on. So there's really lots and lots. Last time we counted, we had ideas, about 40 ideas for new projects and papers. So there's a lot of things going on. We might not get to all of them, but at least it's good to have plans. And so let me end off by saying that I hope I convinced you that pulsars are hugely interesting. It's a rich and diverse field, and we can probe fundamental physics under extreme conditions. You cannot replicate this on Earth in any way. The B fields are too huge. the conditions, the compactness is too much, so the densities. So this is really a unique probe. And they are difficult objects to understand fully. So we're still probing them and understanding and trying to figure out what's going on. There are multi-messenger objects. They give us all kinds of interesting things like photons and particles, and you can look at polarization, which I have not even mentioned, and spin down, the timing, all these things, gravitational waves you can probe. And so there's lots of new telescopes coming online, lots of new discoveries being made, or that will be made in the next decade or so. And also now the algorithms and the techniques to find these pulsars and to analyze them are also growing and becoming better and being enhanced. So machine learning, all these type of things, computer power, that all helps. And so let me end by saying thank you for listening, and I'm happy to answer questions.
Thanks very much, Christo. That was quite intense. Protocol for questions. I think people online, if you can maybe just type it into the chat or put your hand up, click on the icon to put your hand up if you want to speak physically. Any questions from the audience, just ask them to me and I'll repeat them so that it can get onto the recording of the video. Anybody in the audience want to kick off? All right, maybe I can just quickly ask one. What's the closest pulsar to us?
So I know there's some millisecond pulsars. I'm thinking of one that is about, it's sub-parsec, sub-kiloparsec, maybe a few hundred. I think the closest one is about 100 parsecs. So if you have to convert to centimeters, that's 18, it's 10 to the 20 centimeters. So it's close in astronomical terms, but it's still far. You will never see one with your eyes. All you can get is the photons and the particles, hopefully, that come from them. But the photons you can pinpoint because of the periodicity. So those are so small, these objects, that it's like pinpoints in the sky, and you will never actually see them. All of these things I've showed you, this picture like this one, are called cartoon versions. But we do see the pulsations from them.
So are all pulsars neutron stars? And you say there are white dwarfs that can also have a sort of a pulsar. What is a white dwarf? Is a white dwarf not a neutron star?
No, so that's a good question. So if you have stellar evolution and you run out of fuel, then what happens if the star is not too heavy? You can actually implode the star, but you reach a state where the gas inside is made up of electrons, degenerate electrons, and that can produce a pressure, also due to Pauli's principle, and that can stabilize the star, but they are much bigger. I think it's thousands of kilometers across, and those are called white dwarfs. But then if you have the second source of stabilizing pressure, the neutron star, the neutrons inside, that's a neutron star. And if this pressure is not enough anymore, like if you go above about 2 solar masses or so, then this thing will just collapse into a black hole. So yeah, different types of stars. It's quite different. It's not as compact, the white dwarfs, yes.
Okay, and the gravitational wave measurements from the from affecting the pulsars,
Yes.
something new to me. How old is that sort of science? Has it been happening for a long time, or is it something recent?
No, it's quite recent. So, okay, let's start with the prediction. So Einstein predicted gravitational waves early on, and this is about 100 years old, the prediction that we should get gravitational waves. And so people built LIGO and Virgo, these big machines, where it's about a 4 kilometer angle, right angle. Let's say it this way: they have 2 arms, these interferometers, and they are about 4 by 4 kilometers. So they measure gravitational waves from individual objects. But then people realized that there might be many of these objects giving you a background of waves. And then they thought that, well, pulsars are very good clocks. Let's try to measure this background. And so the ideas came, but people really started doing this, I think, about 20 years back, in all intensity and earnestness. There's a whole lot of science trying to figure out which are the best sources to track and how to remove the solar wind effects and all kinds of other atmospheric effects, which stars are stable, which are not so stable, all these things. And yeah, a lot of science going in there, a lot of work, but we are inching closer towards a 5 sigma detection. And that's a different type of gravitational wave detection than the one that got the Nobel Prize. That one was due, the first one was due to merging black holes, but this one is due to a background of waves all over, coming from all directions, isotropically.
Okay, fascinating.
Also, study on the neutron star, where perhaps the angle of the maximum small. What causes the precession? We saw in some of the pictures, these beams are actually rotating.
Yeah, so
what causes it? The origin of it.
So it appears. Okay, just let me repeat the question, Piers, for the recording. So Pierre asked the speed of the pulsar is because it collapses, so that's why it spins very fast. But the precession where that beam is sort of moving in a circle, what is the cause of that? What is the physics behind that?
Yeah, that's an interesting one. I think there's different ideas. It might be, they say that there are very spherical objects, the most spherical objects in the universe. But if there's some kind of sphericity, then that might be some kind of effect that you can create. Maybe it has to do also with the evolution of how this thing collapsed. And sometimes you can induce a kick in the motion of the pulsars, so they have a proper motion through the sky, for example. I'm not totally sure. Maybe some people have theories about what's going on inside, and there's vortices and the neutron superfluid. So I don't think it's clear exactly what causes the precession, but we do actually pick up in some cases some precessing motion in these things, but it's not as common. But I've heard that people look at this and theorize about this, yes. There can also be a torque due to the electric and magnetic field around it, and how maybe if there's a binary companion and there's interaction between the magnetospheres, that can cause a torque, and this can cause precession as well. And there might be a shock that's developing between these two parts of the pulsar system. So you can get electromagnetic torques as well.
Lots of elements there. Okay, another question?
Trying to break it into something as a simple concept. Say, for argument's sake, you stand directly above a lighthouse. Right? You won't actually see the beam of light going around in a circle. The reason why you see the light is because you're at the same elevation as the lighthouse, and it periodically rotates. So it'll flash. But so what I'm saying is that possibly we don't see all the pulses that we might see because of the angle that we're observing it from on Earth. In other words, it may be we may be missing half of them, 3/4 of them.
But so the question is essentially we can only detect the beam if it aims directly or very close to directly at us. So what percentage of them do we miss because we don't actually see them?
Yeah, this is a good question. I have to say that those pictures I showed you is mostly of radio pulsars, so they're very narrow beams of a few degrees. So you're quite right that we might actually miss a lot of them. Maybe we only see 1 in 10. Who knows? There's different models. You have to figure out what the beaming structure is and the beam structure and so on. But the gamma rays, we think, is much, much broader, much wider beam. And we think that we see most of them because it's such a wide beam that it's hard to miss. So they have to be very intrinsically faint or far away for us to miss them. So we think that we see much, much more. And this is an interesting question for people doing population synthesis, because they actually predict these things. They predict a fraction of pulsars you see and those you don't see, those that are radio loud and radio quiet, and gamma ray loud, gamma ray quiet, and all these things. So indeed, I would venture to say that you see most of the gamma ray pulsars and only a few of the radio, but luckily since you see the gamma, then you can look for the radio and vice versa. Actually, it works the other way around. When you see the the radio pulsar, you can look in the gamma ray data and you find oftentimes a gamma ray pulsar. But we do have some of these that are gamma loud and radio quiet, or vice versa. And so we do think this is due to beaming and our orientation with respect to the pulsars. And this is reflecting the beaming geometry of the pulsars, definitely.
Okay. Are the gamma ray sources that HES detects, for example, are there a lot of other sources besides pulsars, or is it all pulsars, or what's the sort of
lots of sources,
gamma ray sources in the sky?
Yeah,
Sorry?
so there's lots of sources that can give you these high energy photons. So usually we split this into two sides. There's the extragalactic type of sources, and those are mostly active galactic nuclei and blazars pointing towards us and so on. And it's a whole field on its own. And then in the galactic science, you see different types of sources, the most numerous being pulsar nebulae in those energy bands. And pulsars are quite a newcomer, and we only have a handful, like 5 of them. But the others, we see about, I think it's 100 TV sources or something, few hundreds now. So it's growing. But in the galactic one, you also see microquasars and binary systems and so on. So other sources as well, definitely. The unique thing for the pulsars is that they are pulsed. So you don't just see an image of some glowing sphere, you see the pulsations, and that is special because then you can clinch the identity of the source, because you know from other wave bands the periodicity and the period. And if you see the same period independently in your wave band, then you know it must be the same source. So that's an extra.
Is there a direct or linear correlation between a pulsar's physical size and its rotation speed, or is it different factors?
Yeah. That's a good question, and it's linear. Basically, how we define the size of the pulsar, not the star, but the magnetosphere, is to say where is the light cylinder, because that that is the dividing point of the termination point, let's say, of the magnetosphere, and that goes like the period, linear with period. So that means like a millisecond pulsar has a small magnetosphere, and the young pulsar has a larger magnetosphere.
Okay, sorry, you wanted a question, Van?
Rotational waves. Now, when the first one was measured, we were very excited. So I was wondering, are there many more now? Are we measuring them? And what kind of astronomical event triggers the gravitational wave?
So Elaine is asking how many more detections have there been of gravitational waves since the first one? And sorry, you say what are the sources for?
Okay, yeah. So there's been a few more detections and plausible detections. I think it's mostly different types of black hole systems. They theorize that it might be a black hole neutron star system sometimes, or a neutron star system. But as to my knowledge, which this is not my field, it's mostly black hole mergers. But again, as I said, that is the one type of measurement they do. But then this pulsar type of measurement is for a background of gravitational waves due to all kinds of mergers of compact objects coming from all sides. But I can't give you a number on the first one, unfortunately. I'm not sure.
Okay, so are there more questions from the audience?
One in the chat.
Assuming that these pulsars are very, very far away. However, if they were closer, would the gamma rays given off by the pulsar actually affect life on Earth and sterilize Earth like on the previous extinctions? Maybe one of the extinctions could have been caused by one of these things to sterilizing Earth.
So the question is from our audience, can a gamma ray be dangerous and from a pulsar, can it be close enough to Earth to actually cause an extinction event on Earth?
That's an interesting question. some people have done some calculations of when you have dark matter halos close by and you have annihilation and you get gamma rays and so on. From the pulsar side, I think luckily they are far away enough not to be dangerous. There are other things like they call them colliding binaries that also produce very high energy gamma rays. So indeed, if you have a source close by, it can be like a blowtorch. It can really impact the Earth and fry us. But luckily, they are far enough that they're not dangerous. But I believe if you scale things and make it close, it's really energetic things these, so it can impact us. But luckily, they are far enough that they are not dangerous.
Okay, then we've got an interesting question from Peter Kotzer on the chat. He says, is it possible to determine the age of pulsars and at what time after the Big Bang did the first pulsars form?
Yeah, so luckily these things we can model them and time them very, very accurately. And so the idea is that they start spinning at a certain birth period and then they spin down. And pulsars are being born all the time. So you see middle-aged ones and young ones, but the oldest ones, if you just take the spinning down effect and you model that, it's called braking radiation because the B field is rotating together with this pulsar and it breaks. It creates a torque on the system, which breaks it. And so that's called braking radiation. So there are some expressions for age of a spin down time, and this goes to 10 to the 10 years. So you can get giga years and even 10 giga years. So neutron stars are an endpoint to stellar evolution. So they are not as early as the earliest stars. You first have to get your star and it has to explode and then it has to. So there's a cycle of burning and fusion and so on. But then soon after, relatively speaking, you would get pulsars being born. And the oldest ones, as I mentioned, are 10 to the 9, 10 to the 10 years old. With a factor of 10 uncertainty, a factor of 5 uncertainty, we don't say that we know everything to a very exquisite accuracy, but the order of magnitude, yeah, giga years. That's what people think are the oldest ones.
Okay, I hope that answers your question there, Peter. Thanks. All right, it's been very, very interesting, very intense. High energy physics, definitely, and high energy presentation. By high energy attention. So thanks very much. It's excellent, and I think I'm going to upload the recording of the video, and it's worthwhile trying to watch again to better understand some of the rapidly disseminated facts there. Anybody got any last-minute questions before we close off? Just quick one from David.
Is there funding available for doctoral and postdoctoral work available in South Africa? To what extent will AI take over or be able to assist with analysis of the data?
So I don't know if you heard that. David was asking about, with all the data now becoming available to astrophysicists, is there funding available for doctorates in South Africa, and how to what extent is AI taking over? I don't know if it can take away the jobs of astrophysicists. I think
yes.
Astrophysicists have to tell the AI what to do.
Yes, no, definitely two answers. The first is that this is fundamental science. We're always looking for funding, trying to do our science, but there's a lot of interesting spin-offs. Eventually, people get a lot of skills. They are useful in the workplace. They can think analytically and do problem solving. They have a lot of skills going into the workspace. So we do have a few options for PhDs and for postdocs. It's also limited by the capacity of the researcher. I have a group of 8 people, and it feels to me that they really take a lot of my time, and I don't want more of them. It's really intense problems, as you can imagine. So to the first question, yes, there are limited positions, but there are some. And if you know people and you look at announcements and so on, at least we do still have money. We're always looking for more. But you will know in the fundamental sciences that sometimes we envy the applications people, the engineering people, and so on, because they can do stuff for industry that we can't, and they can actually generate funding. So that's something we can look into. Secondly, the AI question. I think it's not totally clear. I don't think AI will take our jobs, but AI can assist, and it's our challenge to figure out how to make best use and fair use and ethical use of AI, because we're going to face big data. We're going to have to figure out how to really analyze this big data and read lots and lots and lots of papers and make a picture out of everything. But we still have to think and interpret and model. And I've played a little bit with AI. It's good for creating language, it's language models, but it's not so good at doing math and coming up with interpretations of physical systems. But it's getting better, I'm sure, all the time as it's being trained. So going into the future, I think we cannot ignore AI anymore. We have to incorporate this into our research in an ethical and fair way. And we have to adapt and then try to stay relevant and see what we can still bring to the table as humans and as researchers with hopefully some years of experience. But it's going to challenge us, I'm quite sure, and hopefully enrich us in our work going forward.
All right. Great. Thanks very much for the presentation. Excellent.
Thank you so much. Appreciate your time. Thank you. And if there's any questions that you think of, you can just Google me and email me. I am happy to answer questions that you want to email me. Huh?
Thanks very much. We will do. Thank you. Okay. I'm sure we'll think of a lot more afterwards. All right. Thanks.
That's
Bye.
good. Thank you. Bye-bye.
Thanks everybody for your attendance. And we'll send out the link to the video. Okay. Cheers. Bye.